Okay, hello, welcome back. Good to see you again, early in the morning. Let me recap the main idea from yesterday, which was composition of strategies. And I said that it has a combination of three operations: synchronization plus restarting, or to use a term consistent with process calculus, replication, plus hiding. And a good way to imagine it, to have a mental model of it, is really, if I have a strategy from A to B, I can think of it as a process that has an interface on the right called B and an interface on the left called A. These are not input-outputs. The input, actually, the initial input is here, and then you have a dialogue between the two. And tau is a strategy from B to C, and their composition is a strategy from A to C. This is where the synchronization happens, obviously on B. And also the replication happens because tau can start several copies of sigma. It may require several copies of sigma to interact with if you have a nonlinear function, if you have a function that uses its arguments several times. And we have seen that in general, I left it as an exercise, that composition is always associative. So if I have three strategies that I compose, it doesn't matter if I do it first here or if I do it first here. I always get the same thing. And that is true in general. But where we stopped was at identity. So first of all, what should be an identity? Well, if we think of strategies as I recommended as processes, then an identity is a strategy that goes from B to B, and in some sense, it should behave like a wire, in the sense that whatever comes in here is sent out, whatever comes in here is sent out, right? So there's kind of an interesting anecdote about these so-called mirroring or copycat strategies. As they have been used by pranksters as kind of a trick to play against several grandmasters at chess, and guaranteed that either tie both games, play against two grandmasters and guaranteed that they either tie both games or win one of them without knowing chess. And the first time it was attempted, it was in the 1930s against two Russian world champions, Alekhine and Bogolyubov. And what the prankster did, he played with white in one game, he played with black in the other game, and he just relayed the games, relayed the moves between the two. These were correspondence games. And it was also done live by a British magician called Darren Brown in a room of grandmasters playing live, and again, playing one group against the other just by remembering the moves. In fact, the original prankster who did this trick didn't succeed because the two champions were actually friends, and they found out about this thing and then colluded against him by starting to play really, really weak moves. And then he took the bait and he kind of became overconfident, and he deviated from his own strategy As soon as he deviated, the strategy became unavailable. So then he had to play a proper game, which he failed to win, obviously, because the grandmasters recovered from those intentionally poor mistakes. And that's exactly, the copycat is playing the same role. It's trying to mirror the actions of a strategy in such a way that the composition with it is invisible. It doesn't have any effect on composition. So how do we define something like that? If you have something, because we also have not just the moves to worry about, but also the justification pointers. We have these pointers to worry about, and the role that they play in composition. So let's define it with these intuitions in mind. It is quite faithful to these intuitions. So let's call it the copycat strategy, kappa. On an arena A, it's from A to A. And again, because I have two copies of A, obviously, so I can have an identity both on the left and on the right. So if I have two copies of A, again, I have to distinguish between. There's a coproduct between all of them. So I'm going to tag everything that's here with 0, everything that's here with 1. This, of course, stands for in light of some move, I'm going to write it M0. And in right of some move, I'm going to write it M1. Just to keep the notation more succinct. Right, so what should it happen? And I'm going to give the strategy. Function, which I said for any strategy, we write it like this with a hat. Right, so to begin with, this is going to be the initial move here all the time, and it's going to be some question, and I tag it with 1. And this question is going to have he's going to use some name A, and he's going to introduce some name B. And it needs to be copied. So now it's going to be copied as the same question Q, but on this side, so we tag it with 0. And because these initial moves are justified by these initial moves, this is going to be the pointer used by this move, and every question introduces its own name. Okay? So if I write it here side by side, in the other notation, here I have a move Q, which is copied here, and the pointer goes like this. This is how the copycat strategy starts. This is always opponent, this is always Popeye. And now let's see what happens next. What happens next is we're going to have a sequence of moves that is going to end in a O moves. Let's call it N. And this move, N, can happen either here or there, right? Because if it's a move here, it's going to be copied there by P. If it's here, it's going to be copied in the other side by P. So I'm gonna use the index J to mean that it can be either a 0 move or a 1 move. So J is the tag. And every move has an address, D, a pointer, and it introduces its own address, its own pointer. Now, as I said, if this is an answer move, then this is irrelevant. So for answers, we can ignore this. But just to keep, just so we don't introduce two cases in the definition, one for question, one for answers, I'm just going to put it here, even if it's useless. So that is going to be, so this is an opponent move, so that's going to be copied on the other side. And the other side is the side 1 minus j. But now we need some move. It's going to introduce its own name. But the question is, what should we put here for a name? We can't put this one, because that would break the justification structure. For example, if this is an answer, answers are justifying by a question, so then you will end up with justifying the same thing twice. It doesn't matter. It's not possible. But in fact, even more problematic, this is an O move. This is a P move. O moves have to be justified by P moves, so that move cannot be used also to justify a P move. So this one has to point to some O move. So what is going to be the intuition? The intuition is as follows. We play the copycat game, and at some point n is played, let's say on this side, and is going to be copied on the other side. Again, remember, time, when I write it in this tabular form, time goes down. N was justified by some earlier move, so this is the O, this is the P. N was justified by some earlier move. This was a P move, and we can assume, because that's how we construct the strategy, that this move itself is a replica of an O move happening on the other side. So this was copied here, then something happened, now we get a move here justified by here. This is copied on the other side, so it seems natural that the pointer of the copy move is the copy points to the moves that were copied, right? Does this make sense? It's there is no I cannot give you any let's say mathematical reason why the justification pointers have to be managed the way they are in the copycat strategy. It's just that you want this to be a copycat strategy in the sense that the behavior on the left, so if I just restrict myself to the left, is the same as what happens if I restrict myself to the right. So you see, if I assign the pointers like I just said, if I hide the left, I get a play. If I hide the right, I get a play. And you can see that they are the same. And that's what I want to do. I want to get the same play on the left as the same play on the right. So what I just said now, let's write it as, the important thing is to understand what's going on. I'm going to write it as a definition, just because that's what we need to use when we do proofs, or if we do proofs. We're not going to have time to do proofs, but if you want to do proofs, you need definitions. So you have some sequence P followed by a move M, A, B. So that is going to be the guy that justifies here. So it's going to be in component 1 minus j, and this is going to be the name. Let's also write it as an arrow. That itself is something that has been copied. M D, and now this is on the other side, J, and then some other stuff happens, P prime, and then this happens, okay? So this is how we get the copycat strategy. And we can see that we can quickly check that this is what we wanted by, this is taking too much room, this arrow. Make it a bit tighter to the, we can check that if we take the copycat strategy, if we restrict it on this side, is you get the same thing if you restrict it on this side. So that's what I just said. You can check that this definition implies this fact. And this is what we wanted. We wanted a behavior that looks the same on the left that it looks on the right. And we can quickly check that is a strategy. And the key, I mean, it's going to be, you have to check a number of conditions, and the key condition is that the justification structure of the play is correct, and that will turn out to be correct. Why did we define the copycat strategies? Because we needed an identity. So, theorem, is it the case that this is what we would like to happen, but sadly that's not the case. This is not the identity is not the copycat is not an identity, and this is a technical curiosity that happened in the very first model using this style of game semantics was used by Andreas Blas to give a semantics to linear logic, and there indeed the copycat strategy was not an identity, and you can, to some extent, you can get by with it not being an identity. But if it's not an identity, that means that you cannot use category theory, and that means that certain proofs you have to do them directly to the syntax instead of using category theory as a recipe for models, which is much more convenient. So we really want to have an identity. We don't want to give up on identity. But first, let's see why it's not an identity. Let's give a counterexample. And let's take two strategies, unit to unit. One, we call it sigma bad, and one is the copy unit. And let's first give the sigma bad strategy. It's going to be the following strategy. We call the function, and then the function is going to give an answer. Then, after it gives the answer, is going to inquire about its argument. This is time, let's not forget. Now, what kind of a function is that first returns and then it evaluates its argument? What does it resemble to you? I mean, it's nothing non-computable or anything crazy. I mean, it's an undisciplined behavior, but it's not an absurd behavior. If you think about functions as processes, it's quite reasonable to get an input here, an output there, and then an output here, an input here. Why not? It's a process. It's just a box that has ports, and anything can happen on these ports. So I would say this is a bit like fork in Unix, in the sense that fork will immediately return, but then something else will happen kind of behind the scenes of your thread. And the copycat strategy here that we compose is going to be a question here, and then the answer is going to be copied here. Desynchronization and hiding is going to be happening here. And now can you see what the problem is? Why this is not an identity?
Because A is sort of like dangling.
Yeah, A is, I don't know anything that's going to happen here. In order to have an identity, I should get back QA, QA. But I have no guarantee here that I'm going to get QA, QA. This A can happen either here or here or here. So I get 3 extra behaviors, which is not good. This is not what we want, right? So 3 extra behavior. Let me use a different color to show that this A could happen here, here, here. So it's definitely not a identity. Oh dear, that's a problem. And we have to fix it. And how do you fix a problem like identity? And here, we're moving from the realm of abstract game necessarily into the realm of concrete game models for representing particular languages. Because the solution to this problem, everything up to this point was completely generic, and you could use it for every call by name language. But now, if we want to have an identity, we have to take some measures, we have to make some compromises which are going to make sense only relative to particular languages. Because we need to do a discipline plays with extra conditions. Right now, the only condition that we have on play is that it has a particular justification structure. But we can add extra conditions, basically rule out things like this bad strategy. We can add some conditions to make this strategy, to make this kind of play impossible. So we only restrict ourselves to things that compose well with identity. And B, add closure conditions on strategies. So we already have certain closure conditions on strategies, such as prefix closure. But by adding more closure conditions, we can incorporate more behavior into the strategy. But both of these, we have to be very careful language specific. For example, if you want to model a if you want to model a sequential language, then it is common to add PO alternation as an extra rule here. So first the opponent, then the player, then the opponent, so they have to take turns precisely. And that's exactly how because that's exactly how a sequential term will interact with its context. It will always wait for the context to do something before it does something else. So these are language specific, but here this is a school dedicated to concurrency. So we're going to look at asynchronous games. We're going to look at things that make sense from the point of view of games in an asynchronous setting. So what are these conditions? And so let's look at both of them. There's going to be a condition here and a closure condition here. So the extra condition it's only one. Well, it's only one, but when I'm going to spell it out, I'm going to spell it out formally as two. But informally, it can be stated just as one condition. And these are because of static concurrency. So this is the concurrency that we allow in our language. A command running in parallel with another command. We don't allow fork-like concurrency where you start a command in a completely independent of whatever was. So we don't allow this kind of dynamic, unrestricted concurrency. So here you have to you have a thread that at some point it can fork in two threads, but in order for it to continue, they have to join. So this is the pattern of interaction that we want to capture by our conditions. So fork and join, this is just what I said there. If a thread finishes, then all its sub-threads must have finished. Yeah. So if I go something like C1 parallel C2 follows C3, this C3 will never start before this and this finished. Right? So this is informal, but now let's bring it into the language of games. So I'm going to change the words that bring this into the language of game. If a question is answered, right? Questions is how you start a thread, answers is how you complete a thread. Then it's justified questions must have been answered. Okay? So the analogy between question answers, justification, and threads it's a very strong one. I could move from the I could move from the kind of the informal definition of the condition stated in terms of threads in a lexical way, just by modifying some words.
So, real quick, what's the justification relation between two questions? Like, I was anticipating it would be enabler.
Yeah.
Not, but is that the same relation?
Well, the justification, yeah, they're consistent. The justification is between move occurrences, and the enabling condition is in the arena. But one move in the arena can occur many times in a play. And every instance of that enabling, it's called justification. So let's look at the typical strategy. And in fact, we've already seen strategy for state. So to describe a language of concurrency with state and concurrency, we only have to give one concrete strategy extra, which is for parallel composition. How does parallel composition proceed? Well, it's always going to start on this side with a question, and now we have a question here, an answer here, in any order. I'm going to put a bar between them to show that I don't care in what order they occur. And then finally this. So in terms of timelines, I have the beginning, I have the end, and in this guy can happen in any order. So these are the justification pointers. Right? So you can see if a thread finishes, this guy is finishing, all its subthreads have finished. If a question is answered, all the questions that it justifies have been answered before. And we can express this mathematically neatly by looking at the scope of the names that define the justification pointers. So there are two conditions now. So informally speaking, it was one condition, but now let's break it up to make it simpler into two conditions. The first one, it's called strict scoping. Which says that if I have a play and I have a move which is an answer, this move has a pointer, and answers never justify. So I'm putting an underscore here to mean that there is a name, but we don't care what name is there. And then something else happens, is a play. Then this name A is never going to be used again here. So you really can think, that's the name of strict scoping, you can really think of this answer as kind of ending the scope of the name A. Once the answer has been given, that name goes out of scope, can never be uttered again. The second one is strict nesting. Which says that if I have some move M1 A B, some move occurrence, and another M2 B C, and now I have some answer N B D. So this is a play, and in between I have some other things going on. The important thing is to pay attention to the justification pointers. This goes to here, as does this. And again, N1, this guy, is an answer. Then, see, this is a question which is answered, and it justifies another question. So that means that there must be here, inside this P3, an answer to that M2. So that means that there must be an N2, which is also an answer, such that N, the answer N2, with a pointer C, and again, because it's an answer, we don't care what it introduces, occurs here in P3. Okay? So don't sweat too much over these particular definitions. The point of those definitions is to show you that these ideas can be expressed formally in a nice way, but the important thing to understand is that questions have to be, if the question is answered, then all its sub-questions are also answered. Okay, so that is our extra condition. And it's a condition that makes sense in the following way. Theorem, a small theorem here. If we have this composition where sigma and tau have strongly nested, strongly scope plays, then sigma tau has also strongly nested, strongly scope plays. Okay, so it's just kind of a well-formulous condition showing that we're not doing anything dubious. And now look at, so that was our extra discipline condition. And now let's look at the extra closure condition that we need on strategies. And the closure condition is an established one in all models of asynchronous concurrency. It comes back from models of asynchronous circuits, and the idea is the following. The idea is, what can we synchronize? Things that we cannot synchronize, like if I have two actions in my model, an action A and an action B, and I say in my model that A is followed by B, but there's no way that B can synchronize on A, then I also have to include B followed by A in my model. So I have to include all these permutations of moves that cannot synchronize. So question, when can two moves, or rather move occurrences, synchronize a play? And there are two situations only. The first one let's say M1 and M2 is when I have a pointer. If I have a pointer from M2 to M1, that means M2 is caused by M1. There's no way I can swap them. These pointers always have to point forward. They're causal. They show the cause. The cause has to be in the past, cannot be in the future. Otherwise, if I have an O move followed by a P move, they can also synchronize. P can always synchronize on O, but that's the only synchronization. Think if you play You know, like what a good analogy for asynchronous communication is if you send a letter, right? So if you send a letter, that's a P move. If you receive a letter, it's an O move. So two O moves obviously cannot synchronize because if your opponent, let's say you play 2 games of chess by correspondence, if the opponent says once a move in the first game and then a move in the second game, so O1 followed by O2, well, you don't know that the post office is going to deliver exactly in the same way. So it would be foolish to expect them to be delivered in the same way. You have to be ready for them to be delivered in the opposite way. Maybe the letter that was sent a bit later will arrive a bit earlier. You have no guarantee on that. The same thing with P synchronizing on P. If you send your move in a certain order, you cannot expect your opponent to receive them in the same order because of the same reason. They have different arbitrary bounded delay. So the asynchronous model of communication, whether you look at circuits, whether you look at game semantics, is one of a non-determinate bounded delay. So you know that your move eventually will get there, but you don't know how long it's going to take. On the other hand, you can synchronize on your opponent. I know that I can wait for a move in the first game to happen before I make my move, and then I wait for a move in the second game to happen before I make my move. So the player, the proponent, can always synchronize their actions on V. Anything else has to be swapped. Everything else goes into the closure conditions. And we call it an asynchronous strategy. And these are strongly nested, strongly scoped plays. So if I have some play, just what I said, followed by some move, M0, A0, B0. Let's call this P0, followed by M1, A1, B1. Let's call this P1. Is in the strategy. And M0 is a P move. So this is a P move. Or M1. So if this or this is the case, then we're in a situation in which we cannot synchronize. Because we can only synchronize if this is an O and this is a P. And if we swap them, we got something that's still legal. So P followed by P1 followed by P0 is a legal play. Then P followed by P1 followed by P0 must be as well in sigma. So all the swapping of move occurrences that can be made will be made. If it can happen, it might happen. You have to be prepared for it. And now, with this thing in place, we actually have a category, finally. All the compositions are well formed. They're still associative. We didn't do anything that would violate our initial assumptions. We just restricted things a little bit. So we finally have a category with the identity at A being the least strategy. I'm writing that as strat. That includes the copycat strategy. Why am I writing the least strategy? Because the copycat strategy doesn't necessarily obey this closure condition. It's defined in that way. And that way, by definition, is not necessarily something that respects the closure conditions. But we can make it so by doing that. So it's the least strategy that respects that. Okay? So here, obviously, these two guys cannot be swapped. These two guys cannot be swapped, but things that happen in between here could be swapped. Okay. And this one, you can see that this one is already, by construction, an asynchronous strategy. Because already we said every interleaving here is legal, but I cannot swap these two. Because what would happen if I swap those two? What condition do I violate? If I were to swap this and this. Which one?
Say before the depending finish.
Yeah. Yeah, exactly. So informally it violates this one. Formally it violates the strict nesting. Okay. So now let's describe the language. We have the model of the language. Now we can describe the language and interpret it. What should I? So, is concurrent idealized algo? What do we have in this language? So we have PCF, but I'm going to ignore recursion here. Recursion can be dealt with using a standard recipe, just like I'm going to show you the lambda calculus part of the language can be dealt with using a standard recipe. The same thing with PCF. There's a standard categorical recipe for modeling recursion. Again, categorical means don't get too, people are very intimidated by category theory for some reason, but it simply gives you a recipe for a model. What are the equations that your model has to satisfy in order to be a model for something? So we start with PCF. Local state, so we said that this is a new var operation, and of course you have assignment and dereferencing. Concurrency, parallel composition, I showed you before, plus binary semaphores. So the semaphores are going to be local, just like the variables, and they're going to have grab and release operations. Okay. So you can write a lot of it's a very expressive language. And it has an operational semantics. The operational semantics in the notes. It's completely standard and unexciting. Everything does what's supposed to be done. You know, the state behaves like a state. Concurrency allows you to run either the left or the right non-deterministically, and the semaphores are blocking until they are in the correct state where they can be grabbed or released atomically. And we also have a type system for it. where we write it like this. This is something that has the form x0 has type 0, so on, k has type k. And this is just a simply typed language. So this is the simply typed lambda calculus, and everything here is introduced as a language constant. It can be ground type constants like arithmetic or booleans, or in the case of local state and local semaphores, you have high order constants, which are the new variable that handles the binder, new semaphore that handles the binder. Just to remind you, if I write something like new x in m, that's the same thing as new var of lambda x dot m. Same here. If I have semaphore x in m is the same thing as new sem lambda x dot m. So now let's see why, going back to the initial discussion, why do we need a denotational semantics? We need a denotational semantics because I'm going to challenge you to prove the following. If I have a free variable of command type, new x initialized to 0 in command followed by dereference x is equivalent to command dereferencing 0. Intuitively, why is this true? Because this is just a free variable, so it's going to be bound to some external command, but this is a private block variable, and x here is outside of the scope wherever DC will actually be defined. The only way we can instantiate DC is if we make it into a function, which let's make it like this, make it maybe a bit clearer, make it about closed terms. It's nothing special. Oops. About the fact that it's a free variable. Right? So it's a function that takes a command, has a local variable, initialized to 0, executes the command, then local variable. There's no way this command can change this variable, so I can just say return the constant 0. Now, using first principles, using the definition of observational equivalence, which involves the quantification over all the context, now, go and prove it. And you will find it that you won't be able to. If people, before game semantics was invented, people wrote entire research papers about how to prove stuff like this. You need very sophisticated operational reasonings relying on parametricity. So yeah, let's give you another one. If you, by some miracle, manage to do this one, let's see if you can do this one. Lambda f, new x initialized to 0 in f of x is incremented, so that's the first argument, and then the second argument is the value of x is equivalent to lambda f new y initialized to 0 in f of x is assigned x minus 1 is decremented, and now it's given the negative of the value of x. So this is an up counter, this is a down counter. So whenever f uses its first argument, x will be incremented. Whenever it uses its second argument, x will be decremented. It will be, you just get the value of x. So you have access to x. Now f has access to x, but in a very controlled way. It cannot do whatever it wants. it or read it. On the other hand, here it can decrement it or read the negative of it. And because that's the only thing it can do, you know, if it uses this argument 7 times, this guy is going to be 7. If it uses this argument 7 times, this guy is going to be minus 7, and then you get the minus of it, which is going to be 7. So these two terms are going to be indistinguishable. And this is really first steps towards proving that two, in a very basic setting, something like two modules are equal. Because you have private state and methods at the interface, and they are equivalent. So go ahead and just to amuse yourself, try to prove that equivalence, and you see that you get stuck before you even start. It's very, very hard. But with game semantics, tomorrow we'll show how these get calculated in a rather straightforward way. Right, so let's now interpret this language. And we already know how to interpret all the constants, because we gave the interpretations for state, we gave the interpretation for if, we gave the interpretation for parallel composition. What we need to put them together now is to give the semantics for the lambda calculus. PCF is lambda calculus plus some constants. We know what the constants are, plus some more constants which we know what they are. But terms, to put terms together, you need abstraction and application. So let's look at the semantics of abstraction and application. Basically, the semantics of the lambda calculus. So the fact that we have a model of lambda calculus. So does any of you happen to know what is the categorical recipe to have a model of the lambda calculus? What is it called? You have a category. We already, we have composition, which is associative, and an identity, and that's called a category. When is a category a model of the lambda calculus? When can it give you a recipe to interpret the lambda calculus?
Cartesian closed.
Yes, so it's called a Cartesian closed category. Thank you. Cartesian closed category. And as I said, leaving the fanciful names to the side, it just means that it satisfies certain equations, which I'm not going to give, but those equations guarantee that you have an interpretation of the lambda calculus, and moreover, it tells you what that interpretation is. We need to have product, and we do. We define the product arena. The product must have a unit such that you remember what the unit is? What is the unit for arena products? Do you remember? The empty. The empty arena. So you know what? I told you that the empty arena is not silly. You need it. And you need it because of this. If you don't have a unit, and you don't have a Cartesian product. So you need to come up with this unit. And it exists. We need to have projections. So now we have 3 copies of, sorry, why did I put A1 here? No. I did it. I should just trust my notes. A1, A2, AI, where I is 1 or 2. So that's what I want you to say. Projection I. It's either A1 to A1. Projection 2 is A2 to A2. Sorry? Right? We have projections. What do you think the projection is? If you think of it like this. This is the projection. Let's say projection 1. This is A1. This is A2. And this is A1. Now what do you think the projection should be? Because the projection really should not do much. So what should it be? What is the strategy that doesn't do much? Yeah? Which one? What's it called? Copycat, yes. So it's basically, it's a copycat strategy on A1. So PI is the least strategy that contains the copycat on AI. And notice that the other one is completely ignored. Yeah, you just, because it's going to start here and it's going to go here, just going to go between these two, just completely ignoring this guy. We need to have pairing. The pair of two strategies, so sigma goes from A1 to B, tau goes from A2 to B, and their pairing goes from A1 times A2 to B, and it is simply the union of the two strategies. Yeah? Because if you start here on B, sigma will always talk just to A1, tau will always talk just to A2. And you can now check. I mean, you've seen probably in the type theory lectures the equations that projection should satisfy. And you can convince yourself that pairing and projections behave as they should. What else do we need in our categorical recipe? Exponential arena. Which is used to interpret the arrow. Transpose. If we have a strategy there exists a strategy always this shape. And again, in one of the previous lecture, we looked at how this arena and this arena are isomorphic. There's only a difference between them of relabeling. If you apply that relabeling of moves in sigma, you get the transpose strategy, lambda sigma. And finally, we have an evaluation strategy which goes from right? It's the strategy that is going to interpret function application. So it gets a function and it gets an argument and it produces the result. So let's look this kind of box you have a function which is an A and a B, and then you have an A, and you have to produce a B. Well, what should happen here is the play is going to start on this side, B, and the only thing reasonable that can happen if you're asked, well, what is the overall result? You have to ask the function, what is your result? So you have a copycat strategy here. This guy and this guy are going to talk to each other, just relay information back and forth. And now, at some point, the function is going to ask you, what is my argument A? And all you're going to do, you're going to relay that information to this guy. These guys have to talk to each other. And there's no processing going on. It's just copycatting. Everything that happened here gets copycatted from B to B, from A to A. That's all that happens. So all the, as you can see, all the structural morphisms, the morphisms that interpret the lambda calculus are copycat. The projections are copycat, and the evaluation is copycat. These are the key strategies. So the evaluation is basically the Lee strategy that includes the copycat on A and the copycat on B. That's it. So we have the recipe, and we can use the recipe now to interpret our language. And it's going to be very easy because we did a lot of work, and now everything is going to fall into place very neatly. First of all, we have to interpret our base types. Well, natural numbers are going to be interpreted as the natural number arena. Variables are the variable arena, and so on. We have already defined those. These are very simple arenas with just some questions and some answers. Functions are interpreted by the arrow arena. And this is, by the way, I'm just using the general recipe of Cartesian closed categories. Like if you know how lambda calculus is interpreted in a CCC, I'm not saying anything new. I'm just writing down the standard recipe. In some sense, it's almost redundant. You will find this in any paper on CCCs. The environment is the product. Okay? And we are going to interpret judgments, type judgments. So the first one is the identity. Well, this would be the case projection. Or, concretely speaking, the Lee strategy that has the identity, the copycat on the kth component. Function application. Well, let's do abstraction because it's easier first. This is interpreted using transposing, using transposition. And now abstraction. Sorry, I did that. M applied to n of type theta. I'm going to be pairing M gamma stays the same, so I'm not going to write it, but I'll write the types. M is of type theta prime to theta. N is of type theta prime. Composed with the evaluation morphism. And now to make it more concrete, how do we do it? So this is just union of the two strategies and composed with a least strategy containing the identity at theta union the identity at theta prime. And finally, we have our constants. The constants are defined just as we said. So if I have some constant, let's call it M0 of 0, that's just going to be the strategy for that thing, which we have already defined. Like we have seen what the strategy for addition is, we have seen what the strategy for constants, the strategy for new variable, and so on. Okay? So in the 5 minutes left, let's look at one of the examples, the first one, and I'm going to leave the second one as an exercise. And by the way, I'm not going to do all the calculations, but what I'm going to show you now, it's actually very suitable for automation. And me and some other people have implemented model checkers for these kind of equivalents based on game semantics, because game semantics is very formal, so you can formalize these traces very precisely. Then you can compute with them. But computing by hand is a bit tedious because the definitions are a bit intricate. The definitions are very good for a computer. Things like, the hiding, the selecting, all that. It's a bit hard to do by hand. But I'm gonna do it as quickly as I can in 3 minutes. So how are we going to do this? Well, we know first that this is just the transposition of C composed with 0. What is C composed with 0? Well, it's going to go from a command to another command. This is C. And then we have 0 that goes from unit to some natural number. This is 0. And from these two together, we have sequential composition, which composes a command with a natural number, and you get a natural number. So how is this overall composition going to go? We're going to have a question here, which is going to be copied by the sequential composition here. First, it's going to execute the first command. This is a copycat, so it's simply going to ask the command to execute. The command eventually will terminate, and the copycat will copy back. Now we're in the sequential strategy. The first argument has finished, is going to ask its second argument to execute, this is the 0. So it's going to produce 0. And the 0, because it's sequential composition, is going to produce 0. And in the composition, everything that's in the middle is going to be hidden. So what we are going to get is transposition of the strategy that contains question, and then question of command C, let's write it QC, the answer of command C that says AC, and then 0 at the end. Okay? The second one, I think I started 3 minutes later. So. The second one is a bit more intricate. So it's going to be the transposition of new x is initialized to 0 in C composed with the value of x. So what do we have? We have C, that is command to command. We have x, the dereferencing operation. So that goes from var to nat. So that's the dereferencing. Sequential composition give us the natural number. And now the variable, I'm going to write it a bit more informal because otherwise I would have to do another transposition corresponding to lambda x dot this. But I'm going to make it a bit more informal, saying that this combines to a new variable eventually. So what is going to happen? The same here. It starts here, sequence, do the C, finish the C, finish the C. Now ask the value of the variable. That's going to be copied here. That's going to be copied here. And because, so this is new variable is a constant. So it's written like this. So now the new variable is going to get, because it's a read request and it's initialized to 0, it's going to respond 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 to 0. And everything here is going to be hidden. So in the end, you get the least strategy that has the same thing, Q, QC, AC, AC, 0. Okay? So the point is that instead of doing some kind of a complex inductive reasoning, logical relation, whatever, you can just compute. It's a tedious computation, which I don't recommend to do by hand, but it's a computation that can be and has been automated. So you can write a tool where you plug the two terms and the tool will tell you if these two terms are equal or not. Tomorrow I'm going to talk about, so in this is more or less sound by construction because we're using the strategy. I'm going to talk a little bit about what soundness is without going into the details. I'm going to talk about the definability because this is the strong suit of game semantics. And then I'm going to give you an overview of applications of game semantics. Okay? So, any questions to conclude? Well, thank you.